Okay, so here I'm going to prove this little lemma 6.f, which is a lemma that we used in our proof of theorem 6.11, and a lemma that we may well use again and that you might find useful too when you're working on your assignments. Alright, so what does it say? It says that if for each s and t in the ith subinterval of a partition, the distance from f of s to f of t is less than or equal to epsilon, then the distance from capital M sub I of f and little m sub I of f is less than or equal to epsilon as well. Okay, so if capital M sub I happens to equal M sub I, then we are done. Why? Because if these are equal, then the difference is 0, which is certainly less than or equal to epsilon. So we'll suppose that little m sub I is strictly less than capital M sub I. Remember, little m sub I is the infimum of all values that f takes over the ith subinterval. Capital M sub I is the sup of all values that f takes over the ith subinterval. So little m sub I is always at least less than or equal to capital M sub I. And so, if they're not equal, we have this. Alright, so let me just draw a little picture here along the side. So here we have our little m sub I, and here we have capital M sub I. And we're going to take delta so that delta is less than half the distance between capital M sub I and little m sub I. Alright, so let's write that down. So take delta bigger than 0 such that delta is less than 1/2 the distance between capital M sub I and little m sub I. Alright, well, the reason we do that is because then if we consider little m sub I plus delta, excuse me, here we are, little m sub I plus delta, and capital M sub I minus delta, we notice that little m sub I plus delta won't be more than this point here, the midpoint between capital M sub I and little m sub I. Why? Because remember, this is half the distance between little m sub I and capital M sub I. And also, capital M sub I minus delta will be above this midpoint. In particular, if we do this, little m sub I plus delta is going to be strictly less than capital M sub I minus delta. And that's the only reason that we add this little restriction here. I just want this number, essentially I want this number delta to be small enough so that little m sub I plus delta is less than capital M sub I minus delta. Arbitrarily small, but not so big that this one could be bigger than this one. Alright, well, let's note that, as we said, little m sub I is equal to the infimum of all values that f takes over the ith subinterval. And capital M sub I is equal to the supremum of all values that f takes over the I subinterval. So what does that mean? So there must exist elements S0 and T0 in this I subinterval such that this is true, well, such that f of S0 is less than m sub I plus delta, and capital M sub I minus delta is less than f of T0. All right, well, why is that true? Well, little m sub I, again, is the infimum of all values that f takes over the I subinterval. In other words, it's the greatest lower bound of this set. We add delta to this greatest lower bound. We no longer have a lower bound. There must be an element in this set, in other words, an S0 in this I subinterval, such that f of S0 is less than m sub I plus delta. And similarly, capital M sub I minus delta is less than the least upper bound of this set. That means it's not an upper bound. There's got to be one of these guys, an f of T0, that's bigger than capital M sub I minus delta. All right. Well, let's take a look on our diagram. So our f of S0 sitting somewhere over here, and our f of T0 is sitting somewhere up here. And, as noted before, because of how we chose our delta up here, let's call this star, in fact, because how we chose our delta up here, as noted before, this little m sub I plus delta is strictly less than capital M sub I minus delta. And that's from this little restriction that we put on our delta. So let's write that down. So from star, we know that f of S0 is less than little m sub I plus delta, which is less than capital M sub I minus delta, which is less than f of T0. That's just what we have in this picture. And what does this mean? Well, that means that the distance between these two guys is going to be less than or equal to the distance between these two guys. So let's write that down. That's our little lemma 6.b. Right, so by lemma 6.b, okay, make this all into one sentence. So by our lemma 6.b, we can say that the distance between the two in the middle, these two, just to say capital M sub I minus delta minus M sub I plus delta is going to be less than the distance between the two guys on the outside. That's f of T0 minus f of S0. And notice that this is greater than or equal to 0, so we can put absolute values here. And now, well, let's go up and remember what we're assuming. We're assuming here that for any s and t in the ith subinterval, this distance here is less than or equal to epsilon. All right. So that means that in particular, the distance between these two guys is less than or equal to epsilon. So that's less than or equal to epsilon. And so we rearrange this, what we see on the left here, and we'll have that capital M sub I minus little m sub I, and we could say minus 2 delta is less than or equal to epsilon, and then adding 2 delta to both sides we get is less than or equal to the epsilon plus 2 delta. Well, now remember that this epsilon here was fixed, right? We started with a fixed epsilon, and but the delta here was chosen to be arbitrarily small. We put that condition that said that it had to be at most as large as half the distance between capital M sub I and little m sub I, but the delta was allowed to be arbitrarily small, and because of that, we must have, so let's just write, since delta greater than 0 was arbitrarily small, it was chosen arbitrarily small, we obtain that capital M sub I minus little m sub I is less than or equal to epsilon, and that is exactly what we wanted to prove. So that completes the proof.